Hi everyone, my name is Geneviève Haché. I'm a first year PhD student at Carleton University. And currently, it is when you're watching this video, it'll be 2 a.m. where I am because I'm in Tokyo cheering on my brother for the Deaf Olympics. But I'm glad that I can still get to share my master's research with you through this video. So I'll just get right into it. I know that many of us, as toxicologists, know what PFAS is. So I'll just really go quickly through it. They're highly persistent. They build up inside of the body very easily. They cause a lot of health risks and concern. They can cause liver disease, thyroid disease, reduce immune function, reduce fertility, etc. So, since I just introduced the antagonist to the story, I'm going to introduce the setting. So, my project was based off of a paper that was published a few years ago, wherein Conrad and al. Looked at the amount of PFAS inside of different tissues of salmonid species in Lake Michigan, and they found that there was a concerning amount of PFAS in the eggs specifically. And it suggested that there was a maternal transfer of PFAS happening from mothers to their eggs. And so, if we know that PFAS accumulates in fish eggs and that they're toxic to cells, then how do PFAS affect embryo health? What about their development or their survival? So that's what I set out to find out in my master's project. And with this overarching question, what are the impacts of PFAS, maternal transfer, on the embryo development of rainbow trout? So I chose PFAS specifically. It is one of the legacy PFAS, tends to bioaccumulate a lot. In fact, it was the most prevalent PFAS in the salmon species maternal transfer paper I just mentioned. And we chose rainbow trout as it's a migratory fish, greatly abundant in the Great Lakes, also greatly beloved, and it's a common subject in toxicology studies in Canada. So I want to focus on one specific part of my objective here, the word impact. So here, when I say impact, I mean damage. And PFAS can cause damage in biota in a lot of different ways. But here I'll focus on oxidative stress, which happens to be linked to a lot of the health effects that increased exposure to PFAS can cause. So what is oxidative stress? Well, I write here when thievery is rampant because there's one analogy that I love to use whenever I explain this concept. So reactive oxygen species, they're a type of free radical that contain oxygen. And I like to call them children with very grubby, sticky hands because they have an unpaired electron and they will grab that other electron from wherever they please. It does not matter if it's your important macromolecules, they will go for it. And because ROS are produced naturally by your body, you also have natural defenses, and those are your antioxidants. And those ones are your nannies. They say, hey, leave the important adults alone. You want an electron just taken from me, and so the house can keep going as normal. Nobody's under any type of stress. And so usually they live in a nice balance. But let's say there's either fewer nannies with fewer antioxidants or more children around, those are more ROS, then there's an imbalance that forms, and then the children run amok, cause a bunch of damage, and that's your oxidative stress. And it can cause a lot of damage to your cells, lead to apoptosis, lead to chronic diseases in the long term. There's a bunch of markers to look at them. I'm going to talk about them a little bit later on. But essentially, we know that PFAS can generate ROS. So the overarching question is, does PFAS cause oxidative stress during a embryo trout development? That's what I set out to find out. So here's my general methods plan. So I started by exposing unfertilized rainbow trout eggs to 5 different concentrations of PFAS, with the middle part here being more biologically relevant or environmentally relevant. Afterwards, we just set them out to fertilize and fertilize them, and then we set them out to grow as they please. And I came out every now and then to take some samples. It takes about 4 weeks for them to hatch, and took them back to Carleton for some analysis. So here is just a bit of an overview of the first part, the fertilization, the exposure of the eggs to PFAS, and this would not have been possible without Fleming College Center for Innovative Aquaculture Production. They were fantastic. Just wanted to give them a quick shout out before I move on, because they were truly amazing and invaluable to this project. So moving on to my results now. So I have 3 markers of oxidative stress that I went through. I'm going to go through them one by one. The very first one is antioxidant activity of specifically superoxide dismutase. It really is your body's super nanny. It is your front line of defense against ROS, specifically against superoxide, so which is very damaging to cells.
And then superoxide would essentially catalyze this to hydrogen peroxide, which is still damaging to cells, but less so. And then it can be further catalyzed to oxygen and to water by catalase and glutathione peroxidase. But essentially, SOD is known to rise in activity when there's more ROS, so when there's more oxidative stress. So if we know that PFAS generate ROS and that more ROS would essentially equal to more SOD, therefore, if I expose the eggs to more PFAS, I would expect to see more SOD activity. Excuse me.
Not exactly what I saw. So for reference, I'll always keep the hypothesis at the top left. But essentially, this is my first batch of results. This is a time course from 0 hours post-fertilization to 4 weeks, which is right before hatching. And this is at control level, midpoint exposures, 0.3 parts per million and 30 parts per million. This is on a log scale. So first thing we can notice is that the 0.3 parts per million treatment group does have most significant difference from control. It's a common pattern among the other results, and it's not something I'm going to fully discuss just yet. But there's also no clear dose response until hatching within each of these time points. To be fair, there's only 3 points that I'm looking at, but this will also be apparent when I look. Well, this one's a little bit slightly a bit different, but especially over here. So thing is, PFAS affects the transcription rate and the activity rate of SOD. SOD is 3 different isoforms, not just one. So there's SOD 1, 2, and 3, which essentially have the exact same function. They just have different parts inside of the cells or outside. So what I have here are the results for SOD1 specifically. And which means that we're not also looking at the activity that SOD2 and 3 can have. So I have a feeling that here I would have needed to look at SOD1, 2, and 3 to get the full picture of what's going on. So this will be for a future step. And looking over here, we see a bit more of a dose response now. Quite nice, in fact, because it goes directly in line with my hypothesis. So why is it that everything goes as expected after hatching, whereas before hatching, it doesn't? Well, my current hypothesis is that eggs, they're kind of cocooned inside a little shell, and they're kind of protected against the dangers of free-flowing water, like pathogens or thermic shock or physical shock, etc. And so they might be able to deal with the stress that PFAS may cause. But when the eggs hatch, then the hatchlings are exposed to all the stresses of free-flowing water. Everything starts to compound, and then we see more signs
Of stress. This is something we'll be able to determine later on to check it with further experiments. But moving on to my second set of results now, this is glutathione. Glutathione, I call it a tripeptide hero. It's a tiny little protein that's tossed back and forth between its reduced and oxidized state. Its reduced state is also called active. So reduced glutathione can be used by glutathione peroxidase to neutralize hydrogen peroxide. And it then becomes oxidized or inactivated, and then it can then be recycled back to its reduced state by glutathione reductase. But essentially, glutathione is a bit of a reservoir to use in times of need. So if we know that PFAS would generate ROS and that ROS would theoretically lower the amounts of glutathione, then maybe more PFAS exposure would lower the amount of glutathione. Again, it's not exactly what we saw. So you can see here again, it's a little bit
of a confusing set of results, kind of like SOD, where once more, a 0.3 parts per million has the most significant differences from control, and there's no internal dose responses within each of these time points. And again, I'm applying the same type of hypothesis as SOD because glutathione isn't the full picture. It's tossed back and forth between its active and inactive state by glutathione reductase and glutathione peroxidase, which, much like SODs, have been shown to modulate in transcription rate and in activity rate with exposure to PFAS. So if we look at those enzymes too to get a bit of a clearer picture of what's going on here. However, when the eggs hatch, we have a little bit more of a clear dose response, especially actually right before hatching. This is 4 weeks post-fertilization. And so the amount of glutathione actually increases and then after hatching decreases. And I apply the same type of hypothesis here, where before hatching, the fish eggs may be able to handle stress generated by PFAS a little bit more, whereas right after hatching with all the external sources of stress, everything starts to compound, and then glutathione would start to lower because of oxidative stress. And finally, here's the markers of oxidative damage. This is lipid peroxidation. Lipid peroxidation is only present in the cases of oxidative stress. And throughout this entire process, we have the formation of myelondialdehyde, or MDA. So if we know that PFAS generate ROS, and more ROS would equal more MDA, therefore more PFAS would generate more MDA. You know the pattern by now. So didn't really see any significant results in the time course. In fact, it was lower than the level of detection before 2 weeks post-fertilization. So we can conclude there's not a lot of lipid peroxidation going on here.
And same type of thing with 4 weeks post-fertilization and then after hatching. And here finally is my survival curve. And we see that in fact, 0.3 parts per million treatment group has the highest mortality rate. And it also had the 0.03 parts per million and 30 parts per million group have
a trend of having the lowest mortality rate here. So I concluded that there was a non-monotonic dose response of PFAS concentrations on embryo health throughout their development. And we are going to explore these results a little bit more through a master's student who's going to take over my project. In fact, she's already started, so I'm excited to see where this goes. Thank you very much for your attention, and I hope you enjoy the rest of the seminar.